Hello everyone, welcome to my YouTube channel. So yesterday one of my juniors sent me two problems, and these two problems are from CMI Entrance exam 2024, and I found these two problems very interesting, so I thought that I should make a video on this. The problems are really interesting. So let X be a non-empty finite set and R be a z-valued functions on X. Okay, and S be an additive subgroup of R. It is given such that the unity of this R doesn't belongs to X. By the way, this R forms a ring, right? That you can understand easily because you can just do the usual addition and multiplication. So fx plus gx and fx dot gx, and unity is basically is a map from the X to Z, which sends every X to 1. Okay, so this forms a ring. So R is a ring. That is clear. Now S is an additive subgroup of R such that unity is not in S and S is closed under multiplication. That means if you have two elements F and G in S, then their product is also in S, and S is additive subgroup. This is very important. Okay. Now what you need to show is that there exists a X and a P. There is the X in X and a prime number P such that fx is divisible by P for all f in S. This you have to show. This is a subjective problem. Okay. So first we have, so given that X is a non-empty finite set, right? Then we can do this problem by using induction on the cardinality of X, right? So let cardinality of X is n. So first show the base case. Let X is singleton. Okay, and S be an additive group. Be an additive subgroup of R. Okay, additive subgroup of R. Okay, additive subgroup of R and satisfies the condition, right? Fine. So now what you can see is that, say if you take any f, then f of X belongs to Z. Observe f plus g of X is equal to f of X plus g of X. This is in R, right? And since S is a additive subgroup, since S is an additive subgroup, this set collection of fx such that x belongs to X and f belongs to S, this is an additive subgroup of Z, right? By definition, additive subgroup of Z, because here X is singleton, capital X is singleton, right? And so you are considering fx, and fx is an element of Z, and since f plus g also is in S and fx plus gx also belongs to Z, so this is an additive subgroup. Okay, fine. Additive subgroup, that means this, say this subgroup is say G, G is isomorphic to nz for some n. Okay, now if n not equal to 1, then we are done. Why? Because if n not equal to 1, then choose a prime factor of n, say p. Okay, then fx, p divides fx as n divides fx for all f in S. Hence we are done. Right? So only thing we need to show is that n not equal to 1. Why n not equal to 1? See, if n equal to 1, then G is isomorphic to Z. That means there exists a f in S such that fx is 1. Now my set is x equal to singleton S, right? So that means this map fx equal to 1 is unity of R, right? So that skips a contradiction. So that this implies unity of R belongs to X, which is contradiction to our assumption. Contradiction to our assumption, right? So if X is singleton, then we are done. Now we will use the induction, which is simple. So see, so let X is n. So you can write X to be x1, x2 to xn, write x1 union x2 to xn, write x1 union y. Now if for x1 the claim holds, then we are done, right? If for x1 there exists a prime p such that f of x1 is divisible by p for all f belongs to S, then we are done. If not, then S is an additive subgroup, right? Subgroup of R. Then S, this will imply S is R set X. Here this R X means set of all z valued functions from X to set of all z values functions on X. Okay. If S is additive subgroup on X, then S is an additive subgroup on Y also. Why? Because the elements of S, whatever we are doing, we are pointwise multiplying and we are pointwise adding, right? So f plus g of x is fx plus gx, and f plus fx dot gx is defined by, like, f dot g of x is defined by fx dot gx. So that means whatever we are doing here is we are doing pointwise. So that means we can consider S to be an additive subgroup of Ry also. Now by induction hypothesis, we are done. We are done. Right. So this is a very nice problem, and go to the next one. The problem is saying that let R be a ring of all real valued functions on n cross n. Show that R contains a subring isomorphic to R polynomial rings in two variable with real coefficients, this, right? So how do we approach this problem? See, observe how do you construct a subring isomorphic to this? So suppose you choose fg from R, right? Then you can think polynomial ring in these two variable, right? But the only problem is that, see, if you take this, here x and y are indeterminate. That means there is no relation between x and y. There is no algebraic relation between x and y. But if you take any two arbitrary element f and g from R, where f and g both are real valued functions on n cross n, then there might be a relation between them, right? In particular, say if you take g to be twice f, then definitely this will not be isomorphic as this, because then g and f has an algebraic relation. So that means our only goal is to find two fg in R such that there is no algebraic relation between them, right? Fine. Now what is an obvious choice? Okay, so you have f from n cross n to R. This is just a function on n cross n, right? Just a function. You don't need to think about anything. You can just define whatever you want. It's just a function. But you need to think that they should not satisfy any algebraic relation. So one guess is that take the projection map. Projection map means this and this. Sorry. Projection map on first coordinate, and then take the projection map on second coordinate. You can take any other functions like this also. Okay, doesn't matter. You can take in that way also. Okay, now see, then actually f and g becomes n and m, and there is no algebraic relation in between these two functions. Why? See, if there is some relation, that means aij f power I g power j is 0. That means for ij, where I and j are finite. So then aij f of n comma m power I g of n comma m power j is 0 for all pair nm belongs to n cross n. Right? Now take this pair n equal to 1 and m can be anything. Take. Then what will you get? You will get summation aij this power I 1 comma m power j is 0. This will imply summation aij, this is 1, so 1 power I is 1, and this is m, so it is m power j is 0 for all m belongs to natural number. Now see, this is a summation aij x power j is a polynomial with real coefficient, right? Polynomial with real coefficient. That means it can have finitely many zeros. Means it can have finitely many zeros. That means this equation cannot be valid for all n, right? So hence there is no algebraic relation. Okay, so you can take instead of n, you can take just n square. You can take here m cube, n to the power p, anything like that. But my question is that, can you construct f and g in a different type of f and g such that there is no algebraic relation between them, and that will generate actually the subring you want, that subring isomorphic to the polynomial ring in two variables with real coefficients. Okay, can you find such f and g? If you can, please comment below. Okay, I hope this video will be helpful for you. These two are very nice problem, very interesting problem. Thank you. And also one thing I want to mention, that these two problems one student sent me. Okay, so if you want to get some solutions of some interesting problem, you can definitely mail me, or you can definitely contact me with in Telegram or WhatsApp, whatever you want, and send me the questions. If I find it nice, then definitely I will make a solution video and upload in my YouTube channel. Thank you.